Hello, welcome to CS Stories. Thanks a lot for tuning into my channel. And I got a few questions from you, and one question was a really good one. And that question was, how thick is the ice that we are working on, that we are traveling on? And it's a very simple question with a very complicated answer. And actually, that question was one of the starting questions of the discipline of sea ice physics. And while we always claim that we are a civilian research branch, it's important to remember that one of the main motivations that really led to the big developments in CS physics was the question: how thick is the ice, and can we surface a submarine in the Arctic? Because at the time of between the world wars and the Cold War, it was of very much interest to surface a submarine in the ice between Russia and Canada and the US. So it's a very important question, and let's tackle this question. So first of all, it depends. Sea ice is very variable. So if I have determined the thickness here at this spot, just 1 meter further, it can be completely different. Even we professionals are sometimes very surprised by this variability. So in principle, there's two mechanisms for ice to grow. First of all, ice gets thicker over time. When it's sufficiently cold, then the seawater freezes, and that freezing seawater is basically growing the ice. So now obviously when the ice grows thicker, the ice also insulates from the cold temperatures in the air. So this growth is very fast in the beginning. In the very first days, it's growing extremely fast, and then the growth gets slower and slower and slower. And there is a point at approximately 2 meter, 2 meter 20, depending on the region, where ice cannot get thicker just by the cold temperatures, because at some point winter is over and then ice cannot grow further. So that is the limit for what we call thermodynamic growth of ice. But then there's something else, and that is what we physicists call dynamic growth. And basically that means ice flows crashing into each other, ridging, rafting, piling up, old ice that gets collided with other ice, etc. And there the ice can get much thicker because of the pressure. It can be piled in mountains atop each other, and very often you then measure thicknesses of the ice from 6 to maybe 10 meters. And in extreme cases, particularly when the ice is pushed up against the shoreline, it can even go up to 50 meters for sea ice. This is very rare, but it can actually happen. And you can imagine if then a 50-meter thick piece of sea ice suddenly becomes loose and drifts through the Arctic. That's also quite a big challenge for ships. So that is fortunately very rare, but it does occur particularly north of Canada and north of Greenland. So how do we measure the thickness of the ice? You have already seen in some of my past videos from the last expeditions that there's multiple ways of measuring sea ice thickness. So the most obvious one, or which is also the one that has been used for longest, is just drilling. Basically, you drill a hole through the ice and you put a ruler through and you look how thick the ice is. That's a very easy method, but it has the problem that when you drill a hole here, that you don't know how the ice looks just 5 meters the other direction. So that's why we are using something that is called electromagnetic ice thickness sounding. And here I provide you with a link to one of my videos where you can observe me doing an electromagnetic ice thickness sounding with my colleagues on the last Endurance 22 expedition. And that is basically an electromagnetic way. It's basically you use a metal detector to measure the distance to the seawater. And because sea ice is not conductive, the distance to seawater, if you put the sensor on top of the sea ice, gives you the ice thickness. So that you can not only do pulling a sledge over ground, but you can actually also do it by putting that particular sensor under the helicopter or under a plane. So that gives us long distance transects of ice thicknesses, and we can basically, in very few cases, we can fly from places like in the north of Greenland, from Station North to almost the North Pole, and get a very long transect. And this becomes very important when we talk about the next means of measuring ice thickness, which is the satellite. So nowadays we have very precise satellites up in orbit that can measure the elevation of the Earth down to a fraction of a millimeter. This is either done by laser, so light, or by radar. And yeah, that measures the surface topography of the surface of the Earth. Now you know that any iceberg or also sea ice, obviously, when it's floating, it's sticking out of the water a bit, just like a ship has a part that is sticking out above the water. And if you measure that part that is sticking out, and then you can do a bit of math when you know the density of CS, you can figure out the ice thickness. So basically, you can now measure worldwide distributions of ice thickness with obviously some problems and biases, but we can do that. And here, these other methods are very important to calibrate these satellite sensors. So now I told you that the ice thickness is varying a lot, and uh, what we physicists use to characterize the ice then is something we call the ice thickness distribution. So basically we look at a histogram, so a plot of how often each thickness of ice occurs in our survey area. And this gives us nice curves, and typically these curves have a maximum, what we call the modal thickness. So that is the most frequently occurring ice thickness, which is often related to the ice thickness that comes just from the thermodynamic growth, so when the ice is just growing by cold temperatures. Because the climate is changing, ice in the Arctic is getting thinner. So we know that from satellite observations, we know that from submarine observations, but we also know that from electromagnetic observations. And here are some data from my working group, which have been measuring ice thickness over quite some time, and with using the same devices essentially. And you see that in the 90s, the most frequent ice thickness, so what we call the modal thickness, was between 2.5 to 3 meters, while now in the Arctic in 2011 or also last year, the modal thickness is just down to 1 or 1.5 meter. So there's quite a dramatic reduction in ice thickness going on, which is obviously a bad sign for the state of the climate system. So I hope this brought some light into the question how thick the ice is. And as I said, the answer is not easy, but for most of the time we are actually working on ice that is between 0.5 meter to 3 meters thick, with the occasional ice pressure ridges that maybe reach thicknesses of 15 meters. That is the typical ice thicknesses. And that's it for today. With that, I thank you a lot for watching and have a nice day.